Hi there and welcome from Ventura, California to today's webinar, Autonomous Week Day 3, Autonomous Ground Vehicles, sponsored by Inside GNSS, Inside Unmanned Systems, Hexagon Novotel, Spirent Communications, and QNAV, and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders as today's webinar features expert insights and key technology aspects of sensors, platforms, and integration for implementing autonomy. Today is day 3 of our 3-day series, which focuses on autonomous off-road vehicles with a use case in precision agriculture. Now, we have invited you, along with over 450 professionals registered across 52 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we are confident that you'll find today's webinar of value. Before we do get started, Richard Fisher, publisher Inside GNSS and Inside Unmanned Systems, would like to take just a moment to welcome you and to introduce our main moderator for today's session. So over to you, Richard.
Yeah, thanks, Lori. Welcome all. Autonomous Week Day 3, the culmination of a power-packed set of presentations and discussions we've had during the week. We're excited with the presentations that we're about to hear. We appreciate the sponsorship of Hexagon Position and Autonomy Division of Spirent Communications and QNAV. And we look forward to hearing presentations from them all. So at this point, I will turn it over to Alan Cameron, Editor-in-Chief of Inside GNSS and PNT Editor of Inside Unmanned Systems. Alan, the floor is yours, sir.
Thank you very much, Richard, and thank you, Lori. Thank you to all in the audience for attending. We are coming up to a rip-roaring finish on Autonomous Week. Wednesday, we had intelligence, surveillance, and reconnaissance with UAVs. Yesterday, we did machine control. Today, the theme is autonomous ground vehicles, and we have a special treat in store for our audience today. Well, I should not say astonishing, because we all know what technology is capable of. Still, the platform that you will see revealed in a worldwide debut live internet broadcast today is a remarkable step forward in autonomy-enabled ground vehicles. We'll get to that very shortly. Here's a quick look at our panelists, experts all: Tanner Whitmire from Hexagon Novotel, Rafael Gretsch and Ali Soliman from Spirent Communications, and Andrei Soloviev from QNAV. I'll introduce each of them individually as their turns come up. We will have pauses, as Lori said, midway between Rafael and Ali for some questions, and then a full-on question and answer session at the end with all of our panelists. Lori, let's take a look at our audience for a brief query of their interests and applications.
Yes, let's do that. On the screen, you should see the first of our polls for today. In what sector of autonomous ground vehicles are you most active or interested? So if you wouldn't mind selecting one of those options: precision agriculture, mining, ports and freight, military, or construction. Okay, we've got 33% coming in with precision agriculture, 4% mining, 18% ports and freight, 27% military, and 18% construction. So, Alan, any thoughts on these responses?
Well, I have to remark right off the bat, Lori, I don't think I've ever seen 100% participation in voting in a poll. We usually get 80, 90% of people, but gosh, everybody is alert, awake, and on their toes this morning and willing to engage. We've got a large segment, the largest segment, a plurality, not a majority, in precision agriculture, and we'll have a lot to say addressing that segment. Everything said today will pertain equally to autonomous ground vehicles in the other applications, and I see that military is a great interest or a very active segment. Of course, we know that, and the panelists that we have on board today do have experience in the military sector as well as the others. Let's get on to our first speaker, Tanner Whitmire, Business Development Manager, Hexagon for Agriculture, Hexagon Novotel. Tanner is a leading sales and business development manager in agriculture at Hexagon Novotel with more than 10 years in the corporate precision agriculture field. Combined with his years of experience, hands-on experience managing operations at an actual farm, at Whitmire Family Farms, he understands the challenges facing farmers and the importance of providing positioning and autonomy assured. Tanner, take it away.
Thanks, Alan. Glad to be here, everybody. Thanks for joining in. This has been the next 15 minutes or so talking through autonomous vehicles must navigate safely. First, I'd like to ask the question to ourselves, why must autonomous vehicles navigate safely? Is it due to safety of life? Is it due for efficiency? Or is it just strictly customer demand, right? These are all questions that we continue to ask ourselves as we go through the development for vehicles navigating safely. One item that we are aware of is why navigation safety is important, and that's, as you can see from the images here on the left, we have seen what happens with drivers. So maybe the GNSS position failed and the vehicle took a hard turn and hit a tree, or maybe similar to the image on the right, maybe there was operator fatigue and the operator wasn't aware of the vehicle catching on fire. These are all concerns of and leading factors for why navigation safety is important, which is why we are accelerating our development for when there are no drivers. We understand in precision ag applications that the operation windows are becoming tighter, requiring better efficiency and increased productivity. So to understand where safety is influenced, we needed to understand where we see errors. So we started with evaluating from a positioning standpoint, what could cause position errors. The first error defined was the position error, which is your absolute position, latitude and longitude. As we move forward and vehicles are navigating down the path plan, or in agriculture, we call it the AB guidance line, we have the cross-track error. And this is on-path error from pass-to-pass accuracy is another known term. These are the position error and cross-track error are both with relations to the horizontal accuracy. As the use case requirements for autonomy become further defined, I view that the along track error, the vertical error, will be introduced more to being more of a problem to solve. And as we assess the cross-track error or the position error, understanding that the smaller the error, the better the vehicle is well positioned. So now that we've understood where we can see position errors, what's driving the requirements? And as you can see here on the left, one of the items that's driving the requirements is the safety standards. And I'm not going to go through each one of these standards, but just pointing out that some of these are in the automotive industry, some of these are in the agricultural industry, off-road space. But what's the reasoning that's driving these safety standards to increase their integrity levels? Well, kind of going back from personal experience and growing up on the farm, it was really the use case, right? Whenever I was younger, I was manually driving the tractors through the field. As the use case requirements needed better efficiency, cost for lower inputs, we added a GNSS system, and that allowed us to advance the technology. Well, as the use case requirements force the technology to advance, the safety standards advanced. And so today, as we are working towards transitioning from a semi-autonomous application to a fully autonomous application, which is a result of the use case requirements demand, we must advance our technology. Therefore, the safety standards will be advancing as well. And so we need to start looking at relative localization as the operator is removed from behind the steering wheel. The tribal knowledge of knowing where the vehicle is in relation to another vehicle leaves with the operator, right? So we have to make these vehicles smarter, more intelligent to understand where they are compared to other vehicles, to the implement they may be pulling or pushing, or the crop that they're driving through. Not only does the vehicle need to know where it is from a positioning standpoint, it needs to have the technology advancement of sensing its surroundings and understanding the environment it's in, so it knows where it can drive versus where it cannot drive. And not only does it need to know where it can drive, but it also needs to be aware of the situational awareness. And this is where really the safety comes in. And it's for the safety of life and the task integrity. So if, for example, a autonomous sprayer is driving through an orchard and detects a human, it needs to understand whether it's spraying hazard material or not and actually turn the sprayer off so it doesn't cause harm to a human. Now, in a semi-autonomous application, we can have that fail-safe of relying on the human sitting there behind the steering wheel to turn the sprayer off. But as we go to more full autonomous applications, right, we no longer have that person sitting in the cab, and so the intelligence of the vehicle must be advanced to ensure safety and accuracy is maintained. So understanding the importance of positioning autonomy and advancing the GNSS, when we've evaluated and we understand that the relative positioning sensors typically fail where GNSS performs well, right? So GNSS is great in clear skies, adverse weather. It doesn't matter if it's rain, dust, fog. GNSS is a great solution. However, as we move into autonomy, full autonomy, we will not always have these beneficial GNSS, more favorable GNSS conditions. Therefore, we'll have to rely on the relative positioning sensors to ensure that our navigation accuracy and vehicle safety is able to maintain its integrity while driving through an orchard that may have less favorable conditions. And so this is really where tying these sensors together becomes very important from a sensor fusion standpoint. And so walking through some of the sensor fusion capabilities here, the first ability that where it kind of started was having a human driver, right? I was personally driving family farms tractor across the field, and we needed the use case requirements required us to enhance the hardware, and therefore we integrated GNSS assistance, and that allowed us from a light bar visual guidance system to have our pass-to-pass accuracy be able to go from several meters down to 1 meter. And as the use case requirements continue to advance, we slowly started implementing all of our vehicles to include semi-autonomous abilities. And this allowed us to have the vehicle navigate across the field, allowed us to monitor the planter, monitor the agronomic task that is being done. However, one of the requirements here was we needed better pass-to-pass accuracy. So the technology like our TerraStar X correction services has allowed us to go to that 2 centimeter, go from the 1 meter down to decimeter pass-to-pass accuracy. Now, as we continue to transition to the full autonomous solutions, we must adapt and increase the integrity level. So our pass-to-pass accuracy will maintain roughly the same, if not be more robust and more accurate. But the key here is we need to begin advancing our integrity level. And today, up to this point, it's really been at a 95% integrity level. As we move forward, we'll need to advance the integrity level to a 99.99% or higher to ensure safe navigation. And we're confident we will be able to achieve this through the integrity studies that we have been performing over the last several years on high precision positioning, which has also included experts from universities of Stanford and the Illinois Institute of Technology. And it's this ongoing research that we're confident in being able to achieve in the increased integrity requirements that are provided through the safety protection levels of like AG PLD or the ISO 26262 standards. Now, one of the ways that we are advancing and ensuring that our development work is increasing the integrity and ensuring safe navigation and accurate navigation is you may have seen last Wednesday the Hexagon announcement of the collaboration between Novotel and Autonomous Stuff, both part of Hexagon. So we have pioneered an R&D tractor to ensure our developments and efforts are accurately being demonstrated in the field in real live scenarios, real case scenarios. So on the image here on the left is our demonstrator vehicle that we have equipped starter kits to help advance and accelerate time to market agricultural autonomous applications. And the video here on the right is just highlighting a real small clip of the tractor working autonomously. And as you can see, there's a little bit of dust around, which allows GNSS to be more favorable. However, it is also equipped with perception sensors to ensure that it is aware of the situation and the environment that it's running in. So we've talked about the sensor fusion and the technologies. What I'd really like to get into now is the technology that's really influencing vehicle safe navigation. And starting off with GNSS positioning. So we have adapted and upgraded the positioning system for autonomous vehicles to include dual antennas that leverages our positioning engines align software and span technology that is sensor fusion of integrating our GNSS with the IMU to create a tightly coupled GNSS and inertia solution that also offers data rates up to roughly 200 hertz. This technology is allowing us to increase the absolute position for the navigation accuracy to ensure that the autonomous vehicle can start when on an initial start, can receive a heading, an accurate heading, and requires no vehicle movement for the IMU calibration. With the dual antenna setup, we can essentially turn the vehicle on and take off autonomously. Now, as we continue to expand our GNSS portfolio, understanding we need to enhance the integrity. So we are continuing to add the relative localization sensors and have included the items like LiDAR, camera, other input sensors that will be tied into our sensor fusion processing to our span technology that allows for that safe integrity level of navigation. In addition to the navigation accuracy, we want to increase the safety as well. And so we will leverage these LiDARs, these cameras, these other relative sensors for object detection and classification. And it's these influential technologies that's going to provide the autonomy and position assured solution that will also provide better accuracy at lower speeds, be a more reliable and a more available solution that just your typical GNSS system will not be able to provide. It's pulling all these sensors and fusing all these sensors together that is going to provide that autonomy and position assured solution. And one of the ways that we are looking to help our customers advance their development, accelerate their development, is by we've pioneered these end-to-end assured autonomy and positioning solutions. It's these modular kits that we have integrated into our personal R&D, pioneered R&D tractor, autonomous vehicles that starts out with the GNSS starter kit. And it's the multi-constellation, multi-frequency tracking system that provides the solution availability for positioning, navigation, and timing with a purpose-built ROS driver for the autonomous applications. We've also included and created this Vision Application Starter Kit, which is great for perception and localization and helps accelerate customers developing object classification libraries. In addition to the Vision Application Starter Kit, we've also created this Point Cloud Application Starter Kit, which includes a LiDAR system that is great, again, for the perception localization, but it's great for customers looking to integrate the SLAM technologies or obstacle detection from point cloud algorithms. In addition to these Vision and point cloud kits, we have the Vehicle Safety Remote Controller Kit, which allows a safe remote from autonomous vehicle, right? As vehicles need to drive through a barnyard or just need manual control and they don't have a steering wheel, we can offer the remote control, safe remote control, or as well as e-stop to ensure the vehicle is navigating safely. And then lastly, for customers looking to have a foundation to build applications to overcome numerous challenges, whether it's positioning, localization, perception, or sensor fusion, we have the Accelerating Autonomous Application Development Starter Kit that includes each one of our application kits that's been integrated into our pioneered R&D tractor to help advance our customers' autonomous application development. Again, I'm glad to be here, and I will turn it back over to Alan. Thanks.
Thank you, Tanner, for that look at what is a really exciting development in autonomy, an independent off-road ground vehicle. Here it's a tractor in the field, but again, it's a development platform demonstrating the technology's capabilities to be adapted into many different environments: military, ports, freights, construction, and so on. Particularly interesting to me to see the development of the integrity concept, first seen in aviation. Of course, you have to have absolute assurance on your data when planes are flying around in the air. It's developing now into on-road automobile integrity, equally important, and we see that integrity has an application, has particular relevance in off-road too. We'll have some questions for Tanner at the break. First of all, prior to that, we're going to hear a little bit about receiver characterization from Raphael Gretsch, who is Business Development Manager for Connected and Autonomous Vehicles at Spirent Communications. Raphael has a PhD, and he's responsible for engaging the market and collaborators within the connected autonomous vehicle industry, responsible for establishing links between the sales channels and the business unit in the UK for new PNT and connected autonomous vehicle applications, influencing the Spirent business unit to be timely and responsive to meet new business needs and provide technical and solution expertise. This goes together with the development activity looking for further exploitation avenues to take work from technology demonstrators, which is what we've just seen, from demonstrators through to full product solutions. Raphael, please proceed.
Thank you, Alan, for the introduction, and hello, everyone. So yeah, this will be a double act from Spirent. So in the first half, I will look at some of the challenges and developments for GNSS positioning technology within the autonomous systems. And in the second half, my colleague Ali will show you how all of this fits within a precision agriculture context. So when one is faced with designing a system, they must make sure that it will work as intended within its operational design domain. When it comes to a positioning engine, some of the questions which one might ask would revolve around the assurance that the positioning engine will operate as expected within the environment, if there will be a reliable GNSS signal when the system is in use, and if the position reported by the receiver can be trusted. This then leads to another system design requirement, such as the proper selection of the receiver and the antenna, and how best to tune the positioning engine based on the equipment used and the target location. On this chart, we are seeing the main errors which the environment introduces on the GNSS signal from the satellite all the way down to the receiver. Also, the table on the right-hand side shows the error budget and the expected error introduced by each segment. The good news is that there are already several market available augmentation services such as RTK and PPP, or a combination of both. These augmentation and correction services compensate for satellite orbit errors and for ionospheric and tropospheric delays. The downside of such systems is that they generally assume an open sky, so the effects of obscuration and multipath and the receiver bias must still be accounted for, especially in situations where they are very prevalent, such as in the dense urban areas, forests, and cliff faces. Due to these low altitude challenges, several mitigation techniques were and still are being developed. So what we're seeing here on this slide is that some of the correction or the mitigation solutions can happen along or through different stages of the system. So in terms of the early stages where we're looking at the antenna design, and there are several mechanisms how we can design or place the antennas. We can also start looking at the signal modulation, or how we interpret the signal. Again, like there are several ways of how the filtering happens. We can also look at how we process the signal. So how we make sure that we filter the signal from the noise correctly. Again, there are several algorithms and several ways of doing these. I won't go into all of the details, but they're all here. And also, once we have a signal, we can also have other techniques in order to make sure that we have the context awareness in a way, as already mentioned earlier. And we can also use sensors such as image processing to know if we are actually seeing the satellite, or we are receiving the satellite signal as a line of sight, or if it's obscured and we're receiving it through multipath. We can also check if the signal is coherent, we're getting the right signal, say for example rain coming from aviation. And then in terms of statistical situational awareness and localization, we can also have the maps and the 3D environment model. So now we not just have a position, but we also have a map, and we can localize on the map where we are. Then again, given that we are on the receiver, we are trying to interpret the signals down to a position, there are several techniques like particle filtering and Kalman filtering, which are used in the Fusion engine to make sure that the level of confidence is maintained, and whatever we are interpreting as a position is true and valid. So when when we have to kind of validate a system or design a system, there are several ways to test if the positioning engine is going to work as intended when put in its operational environment. And one way of doing so is by taking the device under test and put it in the field and see how it operates. This has the advantage of being as realistic as it can possibly be. However, it is impossible to repeat the same test due to the varying nature of the environment and to the fact that the satellites are constantly in motion. To have a degree of repeatability, one could decide to use a record and playback system. This would allow for the signals to be recorded and then played back to the device under test. By doing so, the test is much more repeatable and also realistic. The challenge with using a record and playback system is that one is limited by how much they can control in the test, in the sense that they can only use whatever signal happened to be available when the recording took place. Simulation, on the other hand, will allow for a much higher control ability and allow for the use of additional signals which can be generated as needed. So in some situations, going out in the field is challenging, and this is where simulation modeling proves to be more cost effective, assuming that the signals generated in the simulation would correlate well with the ones that we expect in the real world. What we have here, this is some of the experiments that Spirent has done, and what we have here is that we recorded some data and we replayed it back to several receivers. And what is interesting to see here is that even though the same signal is provided to the receivers, each receiver would behave slightly differently, and they would also report a slightly different position. What is even more interesting is the fact that even when using the same signal through the record and playback and also the same receiver, the output still varies slightly, which suggests the stochastic nature of the receiver algorithm. So due to time, I won't go into too much more detail about in this, but we have a publication here, which you're more than welcome to download and read into further details. And yeah, Ali will discuss all of this within a precision agriculture context later on in this webinar. So that's all from my end, and I return back to you, Alan.
Thank you, Raphael. Ali will be coming up in just about 5 minutes. We're going to field a few questions from the audience at this break. First one coming in for Tanner. Tanner, what challenges will the agriculture industry need to overcome before the fully autonomous vehicle, such as you demonstrated, are widely accepted?
Great question. In my opinion, what the requirements there that we'll have to overcome is growers, the farmers, the end users, they're going to need to build the trust in the technology to understand that the technology will work seamlessly in their overall workflow. It's the autonomous application is going to be a piece of the workflow, and they have to understand that it's not going to hurt or cause issues in the other pieces of the workflow that may or may not use autonomous types of technology. And in addition to that is growers are going to have to build the trust that they will have the service and support from their machine manufacturers that is required to ensure that the autonomous vehicles can keep autonomous vehicles running. That the OEM manufacturers can keep their autonomous vehicles running.
Right. Trust, integrity, two key terms that go together. You want to know that it's going to be working right all the time. Raphael, a question for you. What metrics do you use to predict your GNSS performance before starting a mission?
Sure. Yeah. So this is an interesting one. So most people tend to just go out and assume that a GNSS signal will be available. So as we've seen earlier, in autonomous systems, that might not be a wise thing to do. So normally in terms of metrics, people tend to look at the dilution of precision, the number of line of sight satellites available, and the satellite health. And there are some tools available, and even Spirent can help if needed. So there are some, the metrics one can, in a way, predict up to a certain extent how the satellites are going to behave and what kind of position accuracy you would expect. So this becomes critical in critical missions. And I think Ali will show some interesting cases in the coming minutes. So so the metrics are basically mostly the dilution of precision, the line of sight, and how much the satellite health is available.
Right, both of which can be input into a simulation. Tanner, another question for you. What do you envision as the most influential technology responsible for making autonomous vehicles navigate safely and accurately in agriculture?
Another great question. I envision it's going to be a combination of positioning software and robust hardware that's going to influence the safety and increase the position accuracy, integrity of navigation, and time synchronization of all these components, these complex systems, which must work together flawlessly.
Software and robust hardware. I know from working behind the scenes that software, getting different software stacks, getting them to work together to input the data from different sensors, getting all that electronically processed and applied in some kind of artificial intelligence framework is really a huge challenge, and that's where expertise is really needed. Lori, let's have another poll of our audience, and then we'll proceed with Ali after that.
All right. Coming up on that screen is our next poll, and we'd like to hear from you. What type of PNT are you currently using or most interested in using aboard autonomous platforms? Go ahead and select one of those options there, GNSS alone, GNSS plus inertial, GNSS plus correction services plus inertial, or GNSS plus perception sensors, camera, LiDAR, radar, etc. I've got 2% coming in with GNSS alone, 27% GNSS plus inertial, 30% GNSS plus correction services plus inertial, and 41% GNSS plus perception sensors like camera, LiDAR, radar. Alan, what are your thoughts here?
Well, this was a bit of a curveball we threw at the audience because there's one answer here that we didn't allow you to check, which is all of the above, which I'm sure if we'd put it on there, everybody would have checked. We're kind of forcing you to make a choice just to see which portion of the preferred solution works best for you. Of course, GNSS alone is really not going to do it in just about every environment, and the other three candidates are roughly equal, but GNSS plus perception sensors taking the lead. If you're forced to choose between GNSS plus something else, it seems like most of the audience wants some form of absolute positioning, even if it's without inertial, some form of absolute positioning plus some form of relative positioning. And of course, that's where the object detection and avoidance is going to come in. We have another question about object detection and avoidance that I'll turn to at the break. But right now, let's go to Ali's presentation. Ali is Business Development Manager for PNT Technologies and Connected Autonomous Vehicles. testing systems for Spirent Communication. He received an honors degree in electronics and communications from Brunel University London and a master's in telecommunications with business at University College London. He started his career at Spirent as a hardware engineer and since then has held multiple positions within the company, including solutions engineer and product manager. As I said, he's currently business development manager for the Americas, focusing on defining complex solutions and helping customers solve their test needs with Spirent's current and future portfolio of products and services. He's an all-round technology enthusiast with a particular interest in PNT, connected and autonomous vehicles, and artificial intelligence. Ali, let's hear it.
Thank you, Alan, and hello, everyone. The principle behind precision agriculture is really simple. The more that farmers know about the land, the more efficient they can be when it comes to planting, cultivating, and harvesting them. And that can obviously deliver a major boost in farm profitability. By applying the right treatment at the right time at each plant, farmers can make huge savings on inputs like water, chemicals, fertilizers, labors, and fuel. In 2016, a U.S. Department of Agriculture survey found that corn farmers were saving around $25 per acre using precision agriculture technologies like yield mapping and variable rate technologies. Let's now discuss briefly the different precision agriculture technologies available. First, let's look at guidance and steering systems. So semi-autonomous and autonomous vehicles are able to navigate along a preset path within the field. This means that the driver can focus on the cultivating work at hand rather than on steering the vehicle. Then there is land preparation. There are many technologies available for mapping farmland and sampling the soil to understand its chemical makeup and variations. And there are other technologies like yield monitoring and variable rate technology. All these technologies are already evolving to embrace the use of artificial intelligence and autonomy for further efficiencies and cost reduction. Like Tanner highlighted, there are a multitude of sensors used to enable precision agriculture. GNSS remains the only source of absolute positioning and is used heavily in all of those technologies. To increase the operational efficiency of the farm, the integrity and availability of the positioning solution has to be fully tested and optimized. There are multiple challenges that affect the precision and integrity of GNSS in farming environment. For example, multipath and obscuration. The sources of multipath and obscuration in a farm environment could be things like trees or high vegetation, the vehicle carrying the receiver, and even the terrain. For example, in a hilly area, many of the low elevation satellites will be obscured. Second challenge I would like to highlight is space weather and in particular ionospheric scintillation. I will cover this in a bit more details today. And then there are other GNSS vulnerabilities like interference and spoofing, which if not mitigated for or at least detected, could compromise the integrity of the solution. And last challenge to highlight is that farming environment has always evolved, has an evolving landscape. This makes it quite hard to map and predict the performance. Okay, let's now focus a bit more on scintillation. Unlike other GNSS errors, which mostly could be eliminated with multi-frequency and multi-constellation and correction services like RTK and PPP, scintillation is really hard to solve for due to the irregularities it causes the ionosphere. The precision agriculture industry, among others, has been actively researching scintillation effects and developing different techniques for detection and mitigation. As I highlighted yesterday, there are many factors that lead to variation in scintillation properties. For example, time of the day, geomagnetic location, season, and solar activity. In fact, the next solar max is expected in a couple of years, which is more reason to test and ensure your system will cope well under a strong scintillation condition. Equatorial region in particular suffers the most when it comes to scintillation. Deep fading effect is observed on the amplitude of the signal, as you can see on the bottom right hand of the screen in that graph. This real-life example highlights the significant effect scintillation can cause. In this case, it is an oil and gas application. In this example, the system was experiencing about 10 to 50 meters of positioning error and loss of differential correction and even loss of signal. This obviously had a significant impact on safety and also on economical loss. It was estimated that up to $10,000 an hour were lost due to this. Let's now look at some other vulnerabilities that can affect the GNSS signal. For example, jamming attacks. This aim at denying the reception of the genuine GNSS signal by overshadowing them with the noisy waveforms. This can saturate the receiver front-end antenna even when pre-filtering for out-of-band interference is used. The jamming waveforms are typically several dBs more powerful than the GNSS signal. And although GNSS receivers are equipped with an AGC circuit to prevent saturation to their ADC, this has a limited dynamic range output and can therefore decrease the amplitude of the incoming jamming to a certain degree. The graph on the top right-hand corner, on the right-hand corner of the screen, show the number of interference incidents reported by pilots over the last couple of decades. Clearly, you can see that there is steady increase in the number, especially in the last couple of years. This is because access to jamming devices is becoming quite easy. The next vulnerability is spoofing. So spoofing was once extremely hard to do, but recent demonstrations have shown that it's really easy to build a GNSS spoofer from open source software and low-cost components. False location and time reading can have severe impact on the positioning system. Anti-spoofing capabilities are indeed improving, but so are the spoofing techniques and sophistication. It is essential to test for spoofing attacks and ensure appropriate flags are raised when a spoofing signal is received. Important key parameters to consider when simulating spoofing is signal's fidelity of the spoof signal and access to a dedicated spoofing tools and scenarios to help you orchestrate a repeatable and successful spoofing scenario. You will recall that I highlighted this solution in yesterday's session when discussing mining applications. I wanted to show this solution again in today's session as it's also applicable to the precision agriculture test need. For precision agriculture, the user will want a complete test system that cover not only GNSS, but also correction data and IMU simulation. And I think our poor result earlier definitely suggests that and this is to ensure as many inputs to the sensor fusion algorithm are tested in a lab in a repeatable and controlled environment. This solution enables testing for spoofing and interference too, without the need for any additional hardware. For example, multiple interference sources could be placed along the trajectory. The simulator will output both the low-level GNSS signal and the interference signal. And the interference signal is modulated based on how far the device under test is away from the source of the interference. Also, spoofing could be simulated in this setup. There are multiple ways to do spoofing. One of them is having two vehicles in the scenario. One is your device under test, trust the true trajectory, and the other is your spoofer, both simulated at the same RF. To add more realism and credibility to the test solution, external motion generated from a dedicated motion generation tools can be fed to the GNSS simulator. This could be done in real time at up to 1 kilohertz for 6 degrees of freedom motion. The GNSS signal is generated based on the remote motion with very low latency and high fidelity. Another additional to this solution to make it even more credible and more application specific is using 3D modeling to realistically simulate the environment as you see in the video. The effect of the vehicle carrying the receiver is taken in consideration. The moving objects on the vehicles can generate multipath, as we highlighted. Using ray tracing algorithm and 3D modeling, the RF signal is updated in real time with the multipath and obscuration effect. This ensures the RF output is indicative of the signal in the field and obviously reduce reliance on live testing. Finally, I would like to highlight that Spirent, with its more than 30 years experience in the PNT industry, has a complete set of solutions and services that can help you accelerate your development and qualification cycle. Thank you all for listening. Alan, over to you.
Thanks, Ali. We'll return with some questions for you in the session to follow our next presenter. Right now, we're going to go to Andrei Soloviev, PhD, principal at QNAV. Andrei's research and development interests focus on sensor fusion and signal processing implementation for GNSS degraded and GNSS denied applications. He's a recipient of the Institute of Navigation's Early Achievement Award and the RTCA William Jackson Award. Andrei, I know you have some very interesting things to tell us about the use of inertial and various software algorithms to help in these degraded and denied environments. Please go ahead.
All right. Thank you, Alan, and hello, everyone. So I'll summarize the main challenges for positioning, and then I'll talk about sensor fusion approaches, how those challenges can be addressed. So GNSS challenges, obviously GNSS is a very mature technology for enabling accurate positioning even to centimeter level in open sky environments. But when we go in more obstructed environments, then it becomes problematic to do GNSS only positioning. Even for precision agriculture, where there's a little bit of obstruction by trees at the end of the field, enabling RTK capabilities based on GNSS alone can be a problem. And then we go into more challenging cases, such as under very dense canopy or mining applications where GNSS is not available at all. So signal obstructions is the first thing we need to worry about. But then also, Ali talked about it, the jamming and spoofing, they may be not of an immediate concern for civilian applications, but they becoming more and more concern for especially fully autonomous application scenarios. And jamming and spoofing has been a big concern for military applications and military users. So just an example, 3 use cases: precision agriculture, mining, and military off-road vehicles, and where different GNSS challenges play a role. So I think right now for precision agriculture and mining, signal obstructions may be still the main challenges, and jamming and spoofing is not so much. But it is, signal obstructions, jamming and spoofing, it's important for military off-road vehicles. But when we start talking about full autonomy, then I think jamming and spoofing, we have to take it into account across the board for all these 3 example cases that I put on the slide. So let's talk about how those challenges can be addressed. So the good news is that signal obstructions and interference can be very efficiently mitigated via sensor fusion. And maybe even the better news that you actually don't have to use very expensive sensors in order to do that. It can be implemented very efficiently, even with consumer-grade MEMS IMUs. The performance of those consumer-grade MEMS IMUs has been improving quite a bit over the last few years. And just to exemplify, I put some example performance of the STMicro iNeMo IMU, which is a typical consumer-grade IMU at a really $3 range. So what I'm showing here is the drift of the Z gyro in the beginning of the test, and then we did quite a bit of driving, 2 hours and 40 minutes, and then measured the same drift at the end of the test. So the difference, the stability of the gyro drift in this case, is within 20 degrees per hour after 3 hours of driving in various conditions. So it's pretty stable, almost at what used to be a tactical grade level IMU, again at a very low cost. So how can we use those inertials to improve the GNSS and address the challenges that I was discussing previously? So there are 2 approaches, tight coupling and deep coupling. For tight coupling, it's essentially sensor fusion at the measurement level, where you fuse pseudoranges, Doppler, and carrier phase with inertial data in order to bridge over GNSS outages or cases where you maybe have partial GNSS measurements available and you cannot do a complete a position fix based on GNSS alone. So this is where tight coupling helps. So the deep coupling actually takes it one level further, where you use the dynamic aiding from the inertial to help the signal processing of the GNSS receiver. And as a result, what it enables an extended signal accumulation, so you can recover weak signals, signals attenuated by canopy or by jamming, but also I think it's a very efficient approach to mitigate the spoofing, basically eliminate the possibility of a spoofing attack. And I'll talk about it later in the presentation as we go along. So benefits of tight coupling. So for signal obstructions, it can maintain solution with partial GNSS measurements not in an urban canyon, for example, or when you have a complete GNSS outage in a tunnel or in a mine, you can coast over some time using the tightly coupled approach. Jamming, if there's a denial of service for GNSS and the inertial's been pre-calibrated using the tightly coupled solution, then you can coast through the jammed areas. And for spoofing, it actually does not prevent the spoofing attack, the tightly coupled, but it can help you to identify if the receiver is being spoofed through consistency checks. But again, it does not prevent the spoofing attack from happening. So the deep integration, essentially, you keep all the advantages of tight coupling and you add more to it. For signal obstructions, it can recover weak signals and then improve signal availability. Jamming, it can mitigate the jamming to a certain extent, so you don't have to deal with the denial of service. And then spoofing, I think it's a very efficient approach to eliminate the spoofing attack from happening at the first place. So let me show you an example benefit of a tightly coupled solution. So this is an example of a GNSS inertial vehicular engine, or GIF, that we developed at QNAV. And what it does, it does a tight coupling of GNSS, pseudoranges and carrier phase, inertial, and the ground vehicle motion constraints. Uses consumer-grade GNSS chipset and consumer-grade IMU. So this is a performance example on this slide in a long tunnel in downtown Chicago. So it's not an off-road application, but the results are quite applicable to off-road solutions as well, especially for mining applications where there may be extended GNSS outages. So this is an example of where we're getting into the tunnel, and then there's an underground tunnel that goes underneath downtown Chicago, Lower Wacker Drive. And then we drive in within that drive with essentially complete GNSS outage over the entire duration, and then exiting the tunnel at this point here. And the tightly coupled solution maintains fairly reliable navigation capabilities throughout this entire test duration. Okay, so now let's talk a little bit more about the deeply coupled mechanization, how it works and what are the advantages. So at a high level, the GNSS receiver is essentially a matched filter. So you have the incoming signal that's coming in and received by the antenna and downsampled by the RF front end. And the structure of this signal is completely known, but we don't know the signal parameters, code phase, carrier frequency, and carrier phase. So the way the receiver works, it constructs a replica signal, which is a duplicate of the incoming signal, and tries to find the code phase and the carrier parameters to match the incoming signal, to maximize the correlation between the replica and the incoming signal. So it does the multiplication and then integrates the results over a certain period of time. And the longer you can integrate this multiplication result, the weaker signals you can acquire. So the traditional receiver, it actually does the 20 millisecond accumulation. As a result, the signal processing gain remains limited. But when you combine the GNSS signal processing with the inertial, you can extend the integration time to something like 0.1 second or 1 second. And that's your ability to recover the weak signals, suppress jamming and spoofing, improves dramatically. And if you can do it coherently, then you can maintain complete tracking status and complete navigation capabilities, including pseudoranges, Doppler, and carrier phase. So generally speaking, doing the deep coupling requires to redesign the receiver architecture. However, it can be done via a firmware upgrade without the hardware redesign. So I think it's possible to do, and that enables to actually insert the deeply coupled implementation via firmware upgrade. So what you do here, you have 20 milliseconds INQ data, so the receiver needs to provide that 20 millisecond INQs. And then the fusion engine can extend the signal integration during the phase adjustment of this 20 millisecond INQs to accommodate the motion dynamics which is provided by the inertial. So the firmware upgrade, I think, is the way to go. That's the way to insert the deeply coupled capabilities into the sensor fusion systems. Some requirements for the deep integration in terms of the GNSS signal aiding. So we're talking about the coherent integration, coherent signal accumulation within the GNSS receiver to maximize the weak signal recovery capabilities and spoofing mitigation capabilities. So your inertial has to be, in this case, accurate. The inertial aiding has to be accurate at a centimeter level, but also the clock needs to be stable at a similar level in order to support coherent accumulation of GNSS signals. So example clock accuracy requirements, if we limit coherent accumulation to 0.1 second integration, I think in this case it can be done with some advanced temperature control oscillators that are stable at a 10 centimeter per second level or equivalent 10 to the minus 10 second per second level. However, if you go in and try to increase the signal accumulation to 1 second interval, then the clock stability requirements also increases to a centimeter per second, 10 to the minus 11 second per second level. Now let me show you some example cases of the benefits of the deep integration. So here's the first example, navigation under dense foliage and integration with low-cost IMU. So what's good about the deep integration in this case is that you can recover the carrier phase and support RTK under dense tree coverage. And this is an example test scenario, a pretty densely covered off-road or country road going through a dense foliage, and we are able to recover a carrier phase and do precise positioning in this kind of environments. Another example is a jamming suppression. So integration of GNSS, GPS, in this case CA code, and consumer-grade IMU. Position performance, what I'm showing the example results here, it's a test where we injected the broadband jamming with the 40 dB attenuation of GNSS signals, GPS signal, as compared to open sky. So it's a pretty large attenuation, and the deeply coupled solution is still able to maintain positioning accuracy at essentially 1 meter level or better in this case. The third example, mitigation of spoofing. So the benefits of the deep integration and using the long coherent accumulation of the signal is that the signal processing bandwidth narrows down to 1 hertz in this case. And as a result, it becomes extremely difficult for the spoofer to actually get into this 1 hertz bandwidth. The spoofer needs to track the platform that it wants to attack at the centimeter per second level of accuracy. And it's possible to do in theory, but practically it's kind of different. It's pretty difficult. So example test for the spoofing mitigation. So this is a QNAP spoofing simulator where we inject spoofing in software into live sky GPS signals. And the unprotected receiver, it's a position push where the spoofing is implemented around this point here, and the unprotected receiver basically gets pushed into the wrong location without using a deep integration. If we do use deep integration, then the receiver becomes immune to spoofing, and the deep integration output follows fairly precisely the actual motion trajectory. The final point I want to make for sensor fusion, it's in degraded environments. It's very important to implement mitigation of measurement outliers. So we're fusing GNSS data with inertial, but in order to do that, we need to make sure that corrupted GNSS measurements specifically by multipath in most cases, they are excluded from the sensor fusion implementation. So there are two steps that can be implemented: the INS-based statistical gating, where you compare predicted measurements versus the actual measurements and just get rid of the ones that do not agree. But then the second step that we found is pretty efficient is additional adaptive de-weighting that actually incorporates the probability of misdetection, outlier misdetection by the inertial-based statistical gating. Let me show you example benefit of importance of the outlier mitigation, the navigation on the dense canopy with and without outlier mitigation. When you do this outlier mitigation, you do it right. The results are shown on the left-hand plot here. You provide a very precise navigation solution without outlier mitigation. It just diverges very quickly, and the solution becomes very unreliable. So just to conclude, yes, there are quite a bit of challenges for GNSS-based positioning, but I think they can be very efficiently addressed by sensor fusion, and it can be done without really using the very expensive inertial sensors. Consumer-grade inertial does offer quite a bit of benefits in terms of mitigating and addressing GNSS challenges. And all of this can be inserted into the system via software and firmware upgrades, including very powerful, deeply integrated capabilities. And that's all I have to say at this point. Back to you, Alan.
Thank you, Andre. We'll have questions. We have a full lineup of questions for our panelists. Before we get to them, we're going to show you a slide of resources for your continued information from Hexagon Novotel on high precision solutions and product development kits, extensive information from Spirent on their case studies, and an ebook on signal propagation, and information from QNAV on its solutions for GNSS degraded and denied environments. Lori, let's have one more poll of our audience before we get to their questions.
Absolutely. In fact, we do have our third and final poll for today, and we'd love to hear from each of you. What are you most interested in testing for basic system performance, sensitivity, accuracy, TTFF, etc., performance under spoofing and or jamming conditions, standards compliance, such as ISO, SOTIF, or others, or all of the above are equally important? All right, 37% basic system performance, 23% performance under spoofing and or jamming conditions, 3% coming in with standards compliance, and 37% with all of the above are equally important. Alan, thoughts here?
Well, the answers are relatively as expected. Most people are interested in testing the signal quality in its various aspects, followed by spoofing and jamming. There's growing awareness. In fact, I have a question we'll turn to in a little bit about that from the audience. Standards compliance, not so much just yet. I predict that will grow in importance, particularly among manufacturers. And if we take the final all of the above and divide it equally among the three options, just as a way of absorbing it into the data, the conclusions that I just mentioned remain about the same. Standards comes up a little bit more. Let's have questions. Here we go with questions from the audience. The first one is for Andrei Soloviev. Andrei, can you talk about the differences in the fusion that you described, GNSS inertial fusion, in off-road, for example, precision agriculture that Tanner talked about, or other off-road applications, sensor fusion in off-road versus on-road?
Sure. So I think at the high level, there are actually it's no different. The basic principles are the same. How you fuse GNSS and inertial. There may be some I would say minor differences, especially when you start to incorporate motion constraints to improve performance of, when you're fusing with consumer grade IMU specifically, and maybe even high grade inertials as well. You have to be more careful generally for off-road applications. The lever arms could be larger. That could be, you need to take that into account more carefully, but also vibrations can increase for off-road applications, and like the constraining velocity in the cross-track direction and the upward direction. You have to be more careful how you incorporate those constraints into the model. But really, those details are different, but the basic principles are exactly the same.
All right. I have a question that I'm going to field myself before turning back to the experts. Someone has asked, where have consumers reported cases of GNSS spoofing and interference events? Well, it's true that most reported incidents of spoofing and jamming have been industrial as opposed to consumer. There's growing awareness among consumers of jamming. Spoofing is not something on their horizon just yet, perhaps because they don't realize that it's happening. But speaking of spoofing and interference generally, China is a big area of GNSS spoofing, including the mysterious spoofing circles, probably related to shipping. Iran is another area, the Black Sea off the coast of Russia, Syria as well. For more information on the reporting of spoofing and jamming, I want to refer that listener to three sites: gps.gov, which is the government's GPS site, the Coast Guard's Navigation Center of Excellence, NavCen, navcen.ucsg.gov, and finally the European GNSS Agency, gsa.europa.eu. Back to questions for our audience. One here for Tanner, and it relates to obstacle detection. How do you ensure that autonomous vehicles in agriculture detect and take measures to protect wildlife as opposed to persons? I suppose we could expand that to other four-legged forms of life, such as farm life, a cow coming into the field, for example, or something else. Any difference in the way the autonomous tractor detects wildlife or other four-leggeds as opposed to persons in the area of activity, Tanner?
Interesting question, Alan. I personally would be curious to understand the use case requirements on whether the vehicle needs to act differently, on whether it needs to know the difference between a human versus a four-legged wildlife animal, right? Is there an action that the vehicle needs to take once it sees and compares there's a difference? But as far as the measures that we would normally go through our process, it's kind of a four-step process. The first step is the data acquisition piece, and that's going out and collecting images, capturing images of the environment that the four-legged animals could be in, or other different animal life, whether it's humans, personnel, dogs, so to speak. Once we've got a good amount of data captured, then it starts the data classification and labeling process, and that's where we'll go through and tag and do annotation of the data to ensure that we have classified the animal correctly. And then from there, it goes to the third step, which is the application development, and that's building out the algorithms, building out the software, and then the final process would be to simulate and test and go through and identify the false positives or false negatives, and see if that aligns with the use case requirements and meets the safety certification process.
Thanks, Tanner. Ali, a question for you. Is there a way to test when GNSS positioning is going to fail? And here's the rub, also test the fallback mechanisms.
Yes, thank you, Alan. Yes, the answer is really in one word, is simulation. Using GNSS simulator gives you this ability, gives you the ability to control all the different parameters for, the 3 different segments of the GNSS constellation. And you can generate any errors and inject them in the scenario to enable a good test coverage for typical errors or even for rare errors like scintillation. So yes, using simulation will allow you to drive your system to its boundaries and then test the fallback mechanism in place. In fact, we highly recommend such tests, especially post-integration. So yeah, I hope that answered the question.
Thanks, Ali. Now, before proceeding with the next question for Andre, I want to encourage all our panelists to, even if I don't direct a question to you, to jump in if you have something to add to what one of the other speakers has said. I realize that you're all in different sectors, so to speak. Richard has done a great job of assembling a kind of interlocking, complementary panel of speakers, each coming from a different viewpoint. There may not be a whole lot of overlap, but if you have something to add, please just jump in. Andre, can sensor fusion help to mitigate multipath errors?
Yes, absolutely. So basically, when it acts at 2 different levels, for tight coupling versus deep coupling, tight coupling essentially detect which measurements are corrupted by multipath and not use those measurements in a sensor fusion solution. But deep coupling, I believe, and our test data shows that it can actually mitigate multipath errors similarly to the way deep coupling mitigates spoofing. So the multipath kind of acts in some cases similar non-line of sight multipath reflections to spoofing, such as repeaters. And essentially, especially when you're in a dynamic situation where your Doppler is different for non-line of sight multipath versus a direct signal, the fact that you're tracking the direct signal and you narrow your tracking bandwidth to 1 Hertz, it just means the multipath is not going to be able to fit into the signal processing chain of the GNSS receiver, and it's just not going to corrupt the measurements. So the answer is absolutely, and it's, at different level, it offers different advantages, the sensor fusion architecture.
Thanks, Andre. Tanner, doubling back to you, can you talk about the fail-safe to stop the vehicle from functioning for whatever reason that it may detect? How does that work?
Yeah, so I would say there's probably numerous different ways that a autonomous manufacturer can handle this. But I'll talk through the way of how we handle it on our R&D autonomous vehicle tractor. So we've broken it down into 3 different fail-safes. And so alarm 1 would essentially be, let's see, there is an obstacle that has been detected and the vehicle needs to stop. So we will emulate someone pulling on the joystick in the vehicle, or essentially it's emulating the vehicle going into neutral and coast to a stop. The second alarm is understanding if there has been some sort of fault detected, and that could be anywhere from we've detected some sort of object, or we have inquired some sort of electronic malfunction of something. Maybe one of the sensors isn't communicating, or there's debris on the sensor. At that point, we immediately put the tractor's parking brake on, and essentially it's emulating that a person is getting out of the seat. And then the third alarm is essentially if we've ever lost power to the navigation controller, we essentially shut the engine off to ensure that the vehicle is always it can always operate from a safety standpoint. And then as always, we will be monitoring the vehicle from a remote e-stop. And so we will always have the opportunity to, if the person monitoring the vehicle driving autonomously doesn't like something they see, we can manually shut the vehicle down remotely as well.
Good to know on all counts. Ali, are there pre-prepared scenarios or recordings for scintillation that could be used to validate a receiver without having in-depth expertise on that subject?
Yes, for sure. There is something that Spirent. This is something that Spirent have available and is being used across the industry to enable quick and comprehensive tests. We do understand this generation of such test scenario is not a simple job, especially if you want to make it obviously realistic. Therefore, Spirent have both simulated data based on accurate modeling of the atmosphere, but also recorded data and simulated scenarios based on recorded data from the last Solar Max in multiple locations across the world. So please get in touch if testing for scintillation is of an interest. We also have subject matter expertise in this subject and have multiple services to help you characterize your system performance. Even if you don't have a simulator, we can do that test for you as well.
Thanks, Ali. Andre, very briefly, first, someone wants to know what was the test duration in the Chicago tunnel test. I believe I know the answer, but you conducted it, so I'll let you do that. And then please go on to address what level of GNSS signal attenuation can be recovered by a deeply integrated system.
Sure. For the Chicago test, it was about 5 minutes in a tunnel. And in terms of the signal attenuation, basically the results that I've showed with 40 dB attenuation, that's pretty much the limit when we use 1 second coherent integration. It can not go beyond that, but 40 dB you can recover in terms of attenuation.
Okay, a couple more questions for you, Andre. For the tight and deep coupling of GNSS and INS, at what point are GNSS corrections included into the processing?
Right. So basically, when you generate the measurements, pseudo range, carry phase, and Doppler, this is where you add corrections to those measurements. So for deep coupling, you do your for tight coupling, receiver provides those measurements, and sometimes the corrections are implemented by the receiver itself. Sometimes, they provide you the corrections and you have to put it on top of the measurements. But for deep integration, you do your extended signal accumulation first, use the accumulation results to generate the measurements, and then apply the corrections at that point.
And finally, Andre, this will be our last question. How do you treat navigation data bits in a deeply integrated system with extended signal accumulation?
So great questions. So basically, I didn't mention that, but when you extend the signal accumulation beyond 20 milliseconds, the duration of navigation data bits is 20 milliseconds. So if you ignore that and the bits change, -1, +1, then you're going to lose energy if you don't do anything about the navigation data bits. So there are two ways. You can pre-store navigation data in advance because they don't change all that often, and just use pre-stored data bits to wipe off navigation data. Or what we've been doing in some cases, you can actually estimate the data bits. So you can try all the different bit combinations over the signal accumulation interval and choose the one that maximizes the signal energy. So there are two ways: pre-stored data bits or searching for the best bit combination.
All right, thank you, Andre. Well, we've come to the conclusion of the final webinar in Autonomous Week. I hope you all out there around the world have enjoyed it and profited by it. You will see a brief summary of it in an upcoming issue of Inside GNSS Magazine. And of course, you'll get the full recordings and slides via email. You're invited to download them, share them with your colleagues, encourage them to sign up. Registration will continue to be open to continue to download this presentation for a good deal of time afterwards. I want to thank our sponsors, Hexagon Novotel, Spirent Communications, and QNAV for making this webinar possible. Thanks to our generous speakers, Tanner Whitmire, Rafael Gretsch, Ali Soleiman, and Andrei Soloviev. Thanks to you, our audience, for attending, and a fond farewell until the next webinar. Thank you for participating in Autonomous Week. Lori, take it away.
Thanks, well, again for joining us. This is Lori Dearman saying, hope we see you on the next one. Bye for now.